Okay, so let us get started. Then welcome back to our weekly TC CPPCon. I am your host Eisenwave this week once again, but usually we switch hosts and we switch topics every single week, so don't expect this to be the norm. Today's topic is metaprogramming with Constexpr. And for this topic, we will first go through a bit of a motivation. So I will show you metaprogramming and how it works in C++ 98. And after this, you'll definitely understand why we need Constexpr. Then we will walk through C++ 11 and all the way up until C++ 20 and all of the changes that have been made to Constexpr, all of the enhancements to it afterwards. Then there will be Const init and Const Eval, which have been added in C++ 20, as well as some pitfalls that you might run into with Constexpr. And then, of course, something very important, the support for it in the standard library. And all of this should take about 45 minutes. Afterwards, there is going to be a 15-minute Q&A, during which I'm going to answer all of your questions. Yeah, and before, what is programming? Well, yeah, if you're curious, if you need any kind of knowledge prior to this presentation, if you just kind of know C++, you should be able to follow this. So that this doesn't require any kind of super advanced knowledge of the language. Yeah, preprocessor metaprogramming. Anyhow, so let us commence with it then. So, but I thought this is for learning C++. Yet another question. Well, this is for learning C++. Yeah, we're going to learn C++ throughout. Okay, so first of all, let's understand what the problem at hand actually is. So sometimes there is some information which we already know at compile time. However, it is hard or impossible to hard-code this information by hand. So the classic example for something that is hard to hard-code would be a very precise constant, such as pi. I mean, sure, we usually kind of remember 3.14159, that's where it ends for a lot of people, but we would like to have full precision. And so this means we would like to compute pi at compile time, or maybe we need the sine of 40 degrees or the cosine of 50 degrees and that kind of stuff. So it would definitely be useful to do this at compile time and not have to go to some website and hard code it by hand. Sometimes it's outright impossible. So you could have a constant that is dependent on a template parameter, and then it's not actually known to the developer what the constant exactly is. It might be, I don't know, 2 times the size of a type that you're given, or something like that. Or maybe a constant, a non-type template parameter multiplied by something squared. I don't know, could be the case, right? So sometimes you just don't know, you couldn't just put it in your code and as a magic number or so. Then sometimes you could write it out. So for instance, a lookup table, but it would be way too much effort to do this. So if you have a very large lookup table of, I don't know, 1,000 numbers that assists you in programming, then you might still run into a situation where it's just too tedious to write it out yourself. And yeah, that's basically why we need metaprogramming, which is, in short, the definition of metaprogramming is basically programming where you take portions of a program as an input and where other programs are your output again. And we can sort of do this even before Constexpr was ever a thing. We can do this even in C++ 98 to some minor extent. So to demonstrate this, let's go through a very, very basic example. And by the way, this example is so classic, you'll find this exact thing on Wikipedia as well. So we have a function, which is the good old factorial function. And if you don't know what factorial is, basically it computes the product of all of the numbers up until n. So for instance, factorial of 3 is going to be 1 times 2 times 3. That's what it does. And we can implement this very easily in this kind of recursive way. So using the conditional operator, we check whether n is equal to 0. And then, if it is 0, that's our base case for a recursion. So we just return 1 in that case. Otherwise, we return n times factorial of n minus 1. So what this means is for factorial of 3, we return 3 times factorial of 2, which is 2 times factorial of 1, which is, well, 1 times factorial of 0, which is 1. So we end up with 3 times 2 times 1 times 1. And that's it. And you can do this to a certain extent in C++ 98 as well, but it's not fun. And I'll show you why it's not fun. So we already have our compiler set up here, standard equals C++ 98. And let's try to implement some kind of factorial function in this. I'll just enlarge the font. We don't need that much space for it. We'll basically need templates in order to make this possible. So first of all, we take some kind of unsigned n as a template parameter. And we define a struct factorial. Now the thing is that if something is available at compile time, well, for that it needs to be a constant expression, and only sort of enum constants are a way to guarantee that something is a constant expression. So that's why we need to use enum in this particular place. So we can say that we define factorial, oh, well, we need to give it some kind of name. So value is equal to n times factorial of, let's say, n minus 1. However, well, we access the value as well. The problem is right now, this is still infinitely recursive. So that's not very nice. Do I have some kind of error? Did I forget something? Oh yeah, oops. That is definitely a stray semicolon. And now we just need to define the base case. And we can define the base case using an explicit specialization. So I'll struct factorial. However, this is going to be factorial only for 0 in particular. And here we define enum. The value is equal to 1. It's as simple as that in this case. Just another semicolon. Yeah. Now you can see we can kind of do this at compile time. We can do this C++ 98. It is just very, very annoying to do this. And we need a lot of lines. But now, theoretically, you could, for instance, use this in something like an array size. So for instance, if you define some kind of global array, you could do factorial of 5 in here, access the value, and this is perfectly legitimate C++ now. We can see this is, well, now 480 zeros following each other. Not sure if that is exactly correct. It should be correct. There are a couple of questions in Twitch chat. So first of all, what is an unevaluated context? Well, an unevaluated context is a situation. Well, it's a context where something never is evaluated. So for instance, like int x is size of, well, 0. I guess it's a bit of a bad example. That the point is that this 0 here, this is never actually evaluated. If you put a function in here, it doesn't even have to be Constexpr. It just is never evaluated at all. So you can do this to kind of look at return types and that sort of stuff. And yeah, 5 factorial is 120. It says 480 because this is an array of ints. If we were to turn this into an array of chars, then yes, it would be 120. So let's move on. So now we kind of know why this is useful, how we can do metaprogramming. But you've seen it's not particularly fun in C++ 98. I mean, at some point you just have so many of these templates, it looks like XML. And ideally what we would like to do instead is to just kind of put some kind of specifier in front of here, or just evaluate this original factorial function at compile time. And that is exactly what Constexpr allows us to do. So here we get into C++ 11 territory, and we obtain the Constexpr keyword. Now what Constexpr does is, first of all, it implies const for variables. So variables, if they're Constexpr, they cannot be modified anymore. and it implies inline for global functions. So it has some effect on linkage. But these are really side notes. You'll figure out soon enough why this is kind of necessary. The most important thing is it makes our function calls and our variable uses, so the places where we kind of make use of our variables, constant expressions. So if we put something like a Constexpr specifier on our, well, let's just kind of go back, copy and paste this guy. So we can get this back into our code, and if we put Constexpr on here, yeah, this is not going to compile in C++ 98, but it's going to compile in C++ 11, because this is now, yeah, well, I have a bit of a naming conflict, I need to get rid of this one. But now we can simply do, let's say, factorial of 5, and we have a function that can be evaluated at compile time, and all we had to do is put Constexpr in here. We could also create a Constexpr variable, so Constexpr unsigned n equals, I don't know, something like factorial 5, right? This is also perfectly fine, and now the places where we use n, well, that's also a constant expression at this point. So this is just as legitimate. And this is just amazing. We just got rid of all of this nasty template stuff. It is much easier. We basically have the same code as before, just with a Constexpr in front. There was very little effort. So as for the next effect, as a consequence, we can now, as you've seen, we can use it in array sizes, we can use it as template arguments, as switch cases, all the places where you can just use constant expressions. And this also allows constant initialization for any kind of literal type. So it's also kind of important to understand what a literal type is. Namely, it is some scalar type, for instance, an int, or it's a float, or it's a pointer, or it is a class that only contains literal types, or it's a reference to a literal type, or it's a pointer to a literal type, or it is a union that contains only literal types, or it's an array of literal types, right? So kind of you have these this base building block, which is a scalar type, such as an int, but you could, for instance, also create some kind of literal type, like a wrapper right here, right? So this is a very, very kind of useless class, but yeah, now we can use wrapper as a literal type. Only problem is we need to access the X inside of it. And there we go. And that should do the, what? Yeah, that's the problem, because we also need to call this with a wrapper. Another .x is missing. Oh, this is just getting annoying, but okay. Yeah, now it works once again. So you can also have classes that are usable at compile time, which is a pretty big step forward. So it's not just individual variables like int and stuff like that. There are also other things which you can use, but the requirements are pretty strict. And there was a question in chat, you can't modify variables in Constexpr. Not in C++ 11. Just, it's not going to work. No, you can't. An assignment is not a constant expression, so it's just never going to work in C++ 11. You can't assign anything, you can't increment anything, you can't change anything. You can just kind of do math, at least in C++ 11. Okay, and so let's move on then. The amazing things that we have just obtained, all these abilities, they come at a certain cost. So there are some restrictions. First of all, we can't have a void return type. And this kind of makes sense because we can't really assign anything. There's no increment and stuff like that. So a void Constexpr function in C++ 11 would be pretty useless. And member functions also can't be virtual. So yeah, no polymorphism. Certain design patterns aren't going to work, but that's doable. You can work around that. And yeah, all of the inputs and outputs to our function, they have to be literal types. And another restriction is that our function needs to be fully defined before it's used. So if we only have something like a prototype, this is not going to be enough. So this classic idea of defining, let's say, the prototype in the header file and defining the Constexpr function in the source file, yeah, that's not going to work. It's not possible. And yeah. And there's this very interesting rule that, well, at least one set of inputs has to produce a constant expression. So we don't always need to produce a constant expression. So simple example, right? So we have some kind of function that just does some nondescript stuff. Well, let's say we try to return the incremented x. The compiler is not going to allow for this. Guess what happens? Expression plus plus x is not a constant expression. Yeah, that's right, because we can't increment. We can't assign, we can't do any of this. However, let's say we have a second parameter, which is bool b, and we only increment when this is true, then this can be a constant expression now. Because if b is false, then we enter this branch right here, and we don't increment here. So for this input, this is indeed a constant expression then. So for instance, if I do Constexpr unsigned x equals foo of false and 1, well, this should basically equal 2 then. Oh, well, okay, if we already used the name, but you get the idea. This is now going to be equal to 2. We don't see it in the assembly output, but it is, trust me. Then another question. Can you compute the Euler number in a Constexpr function? Well, I mean, I think you can, yeah. I don't really see a reason why you couldn't. It would be a little inconvenient in C++ 11, but I think, yeah, you could. Can you define after using it in the same file? I'm pretty sure it needs to be... I'm pretty sure it needs to be defined before it is used. But I could be wrong here, so let's just kind of make double sure that I'm not talking anything nonsensical. So we'll just copy this function signature right here, move it up, and define this a little bit later. And I'm 90% sure this is going to fail. And yes, it does actually fail. So as I've said, it needs to be defined fully before it's used. And here comes, I've saved the best for last, the one biggest restriction that we have, which is that the only statement in the function that's evaluated is basically a single return. That's all we're allowed to have. So all of this classic stuff that you use in order to program your if statements, your for loops, while, switch, whatever, you know, local variables, all of this goes out the window. You're not allowed to have any of it, just a single return that takes the input and produces some kind of output, right? So the restrictions are severe. Normally, I like to say that the creativity of developers kind of works around a lot of these problems, but in this case, it is just too limiting, and it means that a lot of stuff is either impossible to do in C++ 11 Constexpr, or it's just incredibly inconvenient to do. Yeah, Twitch chat says recursion and ternaries go burr. That's exactly true. You can sort of work around the fact that you don't have loops with recursion, and you can use conditional operators to fix some problems, but yeah, you're extremely limited. And you may be asking yourself why these restrictions exist in the first place. Another question from Twitch chat, by the way. So does return with a lambda work? No, a lambda expression is not a constant expression in C++ 11, so that's not going to work. Yeah, so you can't have lambdas, that's not going to work. And yeah, later versions lift a lot of these restrictions. In fact, we're going to go through all of this. But yeah, well, first of all, I would just like to emphasize the rationale why we have these restrictions in the first place. So first of all, Constexpr effects or computation, compilation. So here you have this compute size function. This returns a size t, and doesn't really matter what it does, right? It could just be something really complicated here. And here we're using this compute size function as the size of a standard array. So this means we don't even know the function signature. We don't know the size of the return type before we evaluate this. Hold on, there's actually a syntax error in here. Yeah, I forgot to remove something in here, right? Just ignore this stuff. The point is, you have a create lookup table function but we don't even know its function signature before we've evaluated compute size, right? And then we use another Constexpr variable, we use create lut here, and it could go on and on and on, right? So you take a Constexpr function, produce a Constexpr output, take that as a template parameter, change some return types, turn that into other stuff that goes into Constexpr functions. You just have this huge interwoven mess, right? And the consequence of the fact that you're kind of manipulating compilation while you're still doing it is that Constexpr functions are interpreted and not compiled. So it's not good enough for a compiler to just, have a single pass, compile everything, be done with it, and then run everything. The way that it normally works, it doesn't here, right? So you need to interpret it. And that also means that it needs to be way, way, way slower, right? So you can see maybe a speed difference of like a factor of 1,000 between your optimized runtime code and the Constexpr stuff. So you should be kind of careful not to do too much at compile time, because it's not going to be particularly fast, unfortunately. And another requirement is that Constexpr functions need to be pure. That's another reason for a lot of these restrictions. If you're not familiar with the term pure function, basically it means that given the same inputs, it'll always produce the same outputs. So for that, it needs to be deterministic, right? So, no pseudo-random number generators here or something that are global, no calls to the Windows API, nothing like that. And it's not allowed to have any side effects. So, no mutation of references, which is also why the assignment operator is not a constant expression, no global variable access and stuff like that. Or, no assignment of global variables, right? So this makes a lot of sense, right? Because, for instance, if you had a standard array of int and compute size wouldn't always return the same output, you would be in big trouble, right? Then what would happen is you look at this once and you have an array of size 4. And then next time you evaluate compute size, you have an array of size 5. That doesn't make any sense. That's complete gibberish, right? So, that will be very problematic. Now, Twitch chat says, just do a PRNG with a seed of __line _underline. You could do that. It's just very easy to run into undefined behavior this way, because Constexpr functions are implicitly inline, and so that means they need to be defined the same everywhere in like all headers. So if you then include it in a couple of places and the line number isn't exactly, hold on, the line number is always the same because it's always the same header. But okay, if you just use a line number, that's not really random. But anyhow, so these restrictions, the point is, well, if you do Constexpr inline, right? If you do Constexpr inline, this is another question from Twitch chat, then it has no effect. It's the same as Constexpr. But anyhow, you've kind of seen that these restrictions are necessary so that we get some kind of sane compilation process which is possible and produces consistent outputs. And C++11, however, lifted a lot of these restrictions which previously existed. So almost all statements are now suddenly allowed. You're allowed to have all your regular tools that you normally use, for loops and if statements and stuff like that, everything control flow. You're allowed to have variables. All of this is now possible in C++ 14. And you can see this kind of opens up the floodgates for Constexpr programming. This is the time when people started realizing, hey, this is actually really powerful and not as inconvenient as I thought. So you have stuff like Constexpr ray tracers. People really got creative with this kind of stuff. But anyhow, let's go through this list of actual changes here. You can do almost anything, but you can't do goto, right? So you can't just jump around arbitrarily in your code. There are no labels and stuff like that, with the exception of case and default inside of a switch. You can't try and catch, so these are just outright impossible to put into a Constexpr function, so that you don't have any exceptions and exception handling. But well, big loss, I guess. You can work around that. Many people don't like to have exceptions anywhere anyways. You can't have inline assembly with the ASM keyword, right? But okay, well, like inline assembly doesn't give you a very consistent compilation process anyways. So the next restriction is you can't have variables of non-literal types, right? This makes a lot of sense. How could you have a constant expression without a literal type? But you can have local variables in principle, It's totally okay. You also can't have any variables with static storage duration, which basically means no static, no extern, that kind of stuff isn't possible. But at compile time, you can arguably work around this one as well. And also to kind of ensure this determinism property, we also are not allowed to have any uninitialized variables, uninitialized members, and that sort of stuff. So yeah, and by the way, another question from Twitch chat: does a switch work? Yes, absolutely. You can have switch, you can have if, for loops, all sorts of stuff. And an older function from Jakob Gamer: I thought the whole thing about Constexpr was that the result was evaluated at compile time, so why must it be interpreted? Well, I mean, I've gone over this, and the problem is basically that you affect compilation. Like with Constexpr, you can change function signatures and change template arguments and do all sorts of stuff, so it's just, it's too complicated to kind of do that in one pass. It just doesn't work this way. But anyhow, we have a lot of restrictions lifted. We now can have void return types, and this actually does make sense because we have increments, we have assignments, a lot of things are also now constant expressions that weren't before. So this is pretty cool, right? We have void return types, very nice. And yeah, this is because we have those extra constant expressions now that are totally valid. And yeah, so C++ 14 was definitely a standard that had probably the biggest impact on Constexpr. C++ 17, not so extremely. But C++ 17 still did kind of update a couple of things. So first of all, you now have inline data members, and Constexpr kind of implies that as well. So Constexpr now implies inline in multiple places. And this is just a convenience thing. So if you have a Constexpr data member, then you don't need to define it as like outside the class anymore. So this is largely just a convenience upgrade, but very nice to have that anyways. Also, closure types, so basically, well, colloquially called lambdas, are literal types now, right? So it's now perfectly fine to have lambda expressions and to have variables with those lambda expressions as types in a Constexpr function, right? So not an enormous change, but it's definitely a very nice one to have. And this is really just kind of an arbitrary restriction that was lifted from C++ 14. I'm not 100% sure why this wasn't the case earlier. But yes, very nice. And also there is now this restriction that only one union member needs to be a literal type. So you could have, let's say, a union of a standard string, which is definitely not a literal, and an int, for instance. And as long as you only ever access the int, that's totally fine. That's now a constant expression. This is, you know, maybe a nice to have. I'm not sure where it would come in handy, but I'm sure some people have made use of this particular feature. And yeah, so there's a question from somebody with a keen eye in Twitch chat. Isn't that last line broken because of the greater than? Yeah, I think I messed that up. I didn't actually try to compile this. I just wrote this out. Yeah, that probably kind of messes with it. This should be parenthesized. But anyhow, one of the big changes to Constexpr metaprogramming in C++ 17 is that you have a Constexpr if statement. And this would look like if Constexpr, right? So that's the syntax for how you do that. And you can use that to basically make decisions at compile time, which massively enhances your Constexpr programming capabilities. So for instance, here I'm writing a function which is supposed to decide which of these types to choose, right? So what maxTypeImpl does is it checks whether the size of R is greater than the size of L, and in that case, it returns a new instance of R. Otherwise, it returns L, well, a new instance of L. Now, the thing about if Constexpr is it's not just a regular if. So the block, right, the statement that is false is just completely discarded. It's just thrown out 100%. It's not instantiated. And so this means that in practice, you know, one of, like, this is either true or false. So only this return R is going to remain or return L. And this also return type is then deduced from whatever we return. So if we return R, so if this condition is true, the return type is going to be R, otherwise it's going to be L. And yeah, this is what I call the type deciding function idiom. I haven't really found a better way for it, or a better name for it. And you can also use an alias template right here to make it a little bit more convenient. So using max type, this just uses decal type to obtain the return type from these, right? And yeah, that's a pretty cool thing. Now you might ask yourself, okay, well, if I want to decide which type to choose, why don't I use standard conditional T, for instance? Wouldn't that be sufficient? And in this particular example, yes, I tend to agree. It would be sufficient. But the problem is that if you use standard conditional T too much, so if you make it nested, if you add more conditions to it, maybe 3 in a row or something like that, it turns into absolute complete spaghetti. Whereas if I just kind of put an else if Constexpr here, right, I can make a lot of decisions with like Constexpr local variables in here. I can put some aliases in here that make it more easy for myself to make this decision. I can do all sorts of stuff in this function, and it's just much cleaner. Whereas if you use standard conditional T, nested, maybe for 3 or 4 different decisions, yeah, you're now basically in a completely unreadable land where if your autoformatter messes things up, you're not going to be able to decipher this salad, and it'll just look like XML at that point. So yeah, you can use if Constexpr to make decisions at compile time, even those that affect types. So very, very, very powerful tool overall that can definitely help you out in some situations. Oh yeah, by the way, yeah, another mistake spotted. It should be max type impl of L and R. Absolutely. I really messed this one up. Yeah, absolutely. This should be max type impl. Yes, and then it would work. Otherwise, it's just kind of recursive. Yeah, another response here says decalval. And this is actually interesting about this. Decalval wouldn't even fix this because there are types which cannot be returned by value because they're not copyable and because they're not movable, right? So I just kind of provided the simplified example right here. And yeah, if you want to fix this, then the best option is probably that you return a pointer to R or you return a reference to R, and then you basically use decal type right here, right? You detect the return type, and then you use standard remove reference T or something like that. So if you don't know what types you're working with, yeah, then what you should probably do is return pointers and references to them and just kind of remove that using some type traits. That should be easy enough. But yeah, decalval wouldn't actually help you out in this case. So C++20, we're now entering territory where we can do almost anything we want at compile time. So there are lots and lots of relaxations to Constexpr in C++20, starting with virtual member functions. So now you can have polymorphism at compile time. That's pretty crazy. You're allowed to have destructors, and I'll also explain why you need destructors in some cases in C++20. Before that, definition of a literal type was basically you're not allowed to have any destructor unless it's like explicitly defaulted or so. So it has to be trivial. In C++20, yes, you can have a Constexpr destructor and handle some kind of RAII resource managing stuff. And yeah, then you are now allowed to have uninitialized variables and uninitialized data members, right? So this goes for unions, this goes for classes, and that's pretty convenient because you don't always want to initialize everything. And that makes the implementations of stuff like optional, standard optional a little bit easier. You're allowed to put try and ASM into your code, but you can't actually evaluate those. So they're not constant expressions, but they can in principle appear in your code. And we've also gotten a couple of really cool functions, so standard is constant evaluated, standard construct add, and standard bitcast that enhance our programming capabilities. But I'll go into more detail, like what these kinds of functions do at a later point. Yeah, there's a question from Twitch chat, or I guess a suggestion: implement standard bitcast in C++98. Yeah, that's not going to happen. The reason why these standard library functions were added is because they're kind of fixing the fact that you don't have reinterpret cast and placement new in C++20. Well, in C++20 Constexpr, right? So there are kind of workarounds for the stuff that is still not Constexpr. And yeah, memcopy, the problem with memcopy is that it accepts a void pointer. And if it accepts a void pointer, then that means you have to convert some pointer to void pointer to call it. And that's not Constexpr, right? So this conversion to void pointer and from void pointer, yeah, you're not allowed to do that. That's not Constexpr. But yeah, if you don't care about Constexpr, yeah, you can totally implement Bitcast in terms of memcopy. That's possible. Then there's another question: how would virtual member functions work? What if the derived type is chosen based on a non-constant condition? Well, if the derived type is, well, I don't know what you mean by that. I mean, the compiler takes, like, the compiler uses the vtables in order to figure out the actual derived type, which is supposed to be called. I mean, obviously, you're not allowed to like call anything that that isn't Constexpr, right? Even though it's polymorphic or so that's not gonna happen. But yeah, it's perhaps important to note that there is tons and tons and tons of sanitization taking place at compile time with Constexpr. So, you know, division by zero, doing anything that's not a constant expression, accessing some uninitialized memory, all of these things, they're basically called by the compiler, it's all sanitized. And if you do these kinds of shenanigans, it just simply won't compile. So that's effectively what happens. But yeah, let's move on with yet another pretty awesome feature. And here's where it gets wacky. Here's where it gets into the territory of how is this even Constexpr? So we can actually use new and delete at compile time. I know it sounds crazy, but it's possible. So the restriction is that within the same constant expression, we have to free all of the memory that we have allocated, right? So if we do new int right here, then before the constant expression is kind of over, we have to delete it. Now, it doesn't have to be in the same function, right? So, you know what, let's just get rid of all this kind of stuff that I've written and demonstrate this a little bit more in detail. And we will need to enter, we'll need to use a certain compiler for this that I don't typically like to use, which is MSVC. But it's the only one that supports this feature at this point. And yeah, that also requires certain flags. So then in C++20. O2 is just max. Yeah, O2 still works. Okay, so this is now fine. MSVC compiles this just fine. No problem here. And we can, for instance, maybe to make this a little bit easier, we can just kind of return some ints and return 0 right here. And let's say Constexpr int x equals use memory. This is perfectly fine now because we are freeing all of the memory before the end of this. And for instance, if you kind of get rid of this guy, right, then it won't compile because the expression isn't a constant expression. Guess what happens? Failure was caused by allocated storage not being deallocated. So basically, we have some memory leak detection going on at this point. Yeah, malloc and Constexpr when is another Twitch question. That's probably not going to happen. I would be very surprised. I mean, malloc is supposed to sort of interact with the OS, and yeah, it's very restricted what kind of new you're allowed to use. So the new has to call a replaceable allocation function. So if you define your own operator new, for instance, yeah, that basically doesn't work anymore. In fact, we could sort of try to do this right here. So like, let's say void pointer operator new, and then just kind of take as well, we kind of have to get that size teeth though. Oh, I'm pretty sure we can just get it off new. So standard size t, we do some wacky stuff in here, like, I don't know, return null pointer. Then this basically, if my theory is correct, this should make this not a constant expression. That's weird. Okay, I'm not sure why it works. I need to look more into this, but yes. Okay, so another question from chat. Would you please comment and elaborate on this more? How can memory allocation happen at compile time? Aren't those somehow specific system call, and a function call should only happen at runtime? I mean, it seems this way, but I mean, the thing is your compiler can sort of just manage all of this memory, you know? The important thing is that before the end of the constant expression, everything gets freed. So, I mean, why not? You know, why not? You can just kind of let the compiler figure it out. That's the philosophy with Constexpr. Yeah, the compiler is detecting all those memory leaks. If you don't free something, it'll tell you that you're doing something wrong. Okay, so let's move on to yet another case of this. So standard string is also a literal type in C++20. I mean, that seems pretty wacky. That seems almost impossible. But yes, even though standard string is dynamically allocating memory, it's still a literal type. And this is perfectly fine code. However, you know, as we've seen, only MSVC. I mean, if you don't believe me, you can just kind of switch to GCC or so. Latest trunk GCC, bleeding edge. Doesn't get any more recent than standard in C++20 or so. What? Did I miss something? Did I? Last time I checked, it didn't work. Am I dumb? Well, the compiler support page still says it's not permitted. Okay, maybe either I'm stupid or I'm exceptionally unlucky in that they added this feature kind of just now or something. Oh, that's very strange. Was it maybe okay, maybe it's my fault. Maybe I just forgot to include new or something. No. Well, that is bizarre. What is it? Has there been an update? I tried to test this before the stream and it didn't work. I guess compiler support has moved on in the last days or something when I've written those slides. That's very strange. But okay, I guess it does work now. Well, yeah, I mean, I can try an older version, just 12.0. What? No way. Maybe I'm missing something here. I have no idea why this compiles, I'm gonna be honest. Totally clueless on this part. It might be a very, very wacky thing. The compiler support page says it shouldn't be possible. And I'm like 90% sure this will still fail to compile regardless. So yeah, this now complains that standard string is not a literal type. So on clang trunk basically and GCC, it should say the same thing, that this is not a literal type. It won't allow you to do this. Might be a standard library thing though. I might have tested it wrong, okay, but the point is some of these features, they're only available on MSVC. Unfortunately, other compilers are simply not that far yet. Okay, and there are two more keywords that have been added in C++20, which enhance your Constexpr programming capabilities further. So first of all, there's const init. And what const init does is it says that a variable is zero initialized or constant initialized. So constant initialization means that, well, basically the value has to be known at compile time. You know, that the right-hand side here, you know, that has to be a constant expression. And zero initialization would just be like having it static but uninitialized, or something like that, right? So constant it basically means that we initialize a value at compile time. However, it remains non-const, so we can still kind of modify it at runtime just fine. And this is kind of useful, you know. There are some places where you'd want to do this. For instance, I don't know, const init, yeah, some type. Well, I don't know. Personally, I haven't really found a use case for it yet, but I'm sure some people find it very useful. And then there's also const eval, and const eval makes a function immediate, which takes Constexpr to the max and basically means that it can only ever be evaluated at compile time. Which also creates some kind of wacky scenario. So for instance, if you have a square function, which is const eval, this just takes an int, returns n times n, then this is going to be an error. because here x is not known at compile time, right? It's x equals 100. It's not const, it's not Constexpr, it's not anything, and so this would basically lead to a compiler error. And another really annoying and wacky thing is that if we want to have, let's say, a Constexpr function that calls a const eval function, that's not permitted. Not if we pass the parameters through, like this right here, right? Because this n could, in principle, not be known at compile time, because we can call Constexpr functions, as you can see here, with non-Constexpr parameters as well. And yeah, and then this would be compiler error. So const eval kind of creates a couple of problems. And there's only one place in the standard library, which I'm aware of, where it's even used, which is for standard source location, right? So const eval is basically something you slap onto a function which is only ever evaluated at compile time and nothing else, where it doesn't even make sense to compile it in any other context, which is rather rare, but you know, does have some uses. It's also interesting to kind of look at some places where Constexpr fails us very surprisingly. So it's important to understand that Constexpr doesn't like magically turn our variables into some kind of metaprogramming constant that doesn't exist anywhere in the program. It still exists somewhere. So this is a very classic example that I like to provide. So basically, I'm very surprised because this has gotten a lot better. The compiler output didn't used to be so good, if I remember correctly. Or maybe this was in a different context. Hold on, marge equals native. Maybe it'll do some vectorization or some wacky stuff. No, that's very interesting. I don't remember this compiling as cleanly as it does, to be honest. But yeah, so here in this select and call function, what we have is a table of 4 function pointers. So what happens is we take this input n, we pick the right function pointer from the table, and we call it. And you'll probably be surprised why exactly we have all of these move instructions here, right? You know, like you've been told Constexpr means you initialize everything at compile time, right? So what's up with this? What's up with all of this, you know, dealing with memory? Yeah, okay. Kind of stays the same with all 3, but whatever, right? Oh, okay. Now we get the compiler output that I was looking for, right? So you get this big mess of basically grabbing some stuff out of memory. You can see you have 2 of these function pointers in memory. It is moving it between XMM registers and stuff like that. It's doing all sorts of wacky stuff, which you didn't expect it to do. And the reason is basically that this Constexpr function, right, it's just, Constexpr here is just a combination of const init and const. If we take Constexpr away, it actually doesn't make any difference at all. It'll compile just the same. Because yeah, the compiler knows that we never modify this and that it's, you know, it's constant initialized. But yeah, the reason why we have to put in so much work to kind of create this table is because it's still a regular variable with automatic storage duration, and so that means it lives in some, you know, it lives on the stack and lives on in some registers, etc. And so even though the compiler basically knows all the values, it knows the contents of the entire table at compile time, it still has to put in some effort to kind of to use it, to put it on the stack, to put it into registers and that sort of stuff. We can fix this by making this static, and in this case we just kind of tell the compiler, hey, this only exists once in the program and has static storage duration, and our worries essentially go away, because now it just just puts this into the code, and we have what we would roughly expect. So this is now a jump at an offset from this table, right? So if this was inlined, it would probably be a single instruction, which is, you know, tremendously better. The takeaway here is basically that just because it's Constexpr doesn't make it some kind of, you know, magical constant that doesn't exist anywhere. It still exists somewhere, and you need to kind of take care of that. I ran into this particular, you know, surprising issue myself, and I could speed up my code by, I think, a factor of like 5 times by just putting a static somewhere. So can make a very big difference. Yeah, and what's also worth mentioning is obviously the support in the standard library. You know, all the things that make Constexpr programming even possible, because if you had no standard library at all, you know, what could you even do? So most containers, algorithms, and utility functions by now in the standard library, so in C++ 20, are Constexpr. Like usually if you look at a function and you kind of think, hey, could I reasonably expect this to be Constexpr? Yes, it is Constexpr. So yeah, there are still certain nuisances, you know, there are still some details that are a little bit annoying. So for instance, standard move is not Constexpr in C++ 11, which introduced move semantics. Why this is the case, I don't know. God knows. I'm sure there is some rationale, there was some kind of defect that made it impossible, but yes, it's still annoying. Standard swap, miraculously, has only been made Constexpr in C++ 20, so that's very annoying. You have algorithms, right? So this whole algorithms library, you know, sort and find, if, and all these kinds of things, they're only Constexprs in C++ 20, and standard swap is kind of a big reason for why this is the case. And so, yeah, so you have standard string, you know, standard vector, standard optional, and all of these kinds of things, they have been made Constexpr, right? The problem is that some of this stuff, effectively, it's not really Constexpr in practice, because you need to use MSVC, you need to use some other kind of special compiler to do this kind of stuff. And one of the most bizarre things is that you still don't have Constexpr math functions, right? So you can't do a square root or something like that at compile time without, well, some workarounds basically. So there's a question from Twitch chat. So if we can have Constexpr function arguments, we could do things like int and then Constexpr int n and return n times n. Yes, so that kind of stuff, and I should probably show it here. There is kind of a proposal for this particular idea. Now I don't know the proposal, but yes, this has kind of been speculated about. The proposal suggests this kind of syntax. So this would kind of be like a template parameter, you know, it would implicitly turn the square function into a template, but you still use regular syntax in order to call this, basically. So this has been proposed. It might make it into C++ 23. I'm not sure about the status of that. Then Point Meet You asks, do the parallel versions of algorithms work with Constexpr in theory? Well, there are some proposals for C++ 23 to make those Constexpr, but in C++ 20, no, those algorithms with custom execution policies, none of them are Constexpr. But, you know, might be. There are more relaxations with every standard, so I guess don't get your hopes down or so. It could be. So then you have, and this is what I've kind of skipped over previously. You have these magic functions which massively enhance your Constexpr programming capabilities. So first of all, you can detect whether you are currently in a constant expression using standard is constant evaluated. And this is pretty awesome, so awesome in fact, that I should yeah, demonstrate this. Now I believe this was include Jesus Christ, I'm out of my element. Where is this? Where is this? We'll figure it out in a second if I didn't include the right thing. I think it might have been utility. Might have been utility. Anyhow, so to demonstrate this, also let's grab something from CMath, you know, from this header where unfortunately you have a whole bunch of stuff you can't use it in Constexpr. So let's say you have some kind of float square root Constexpr function. And you want to make this Constexpr, right? Because it's a reasonable expectation. You would want to compute the square root of something at compile time. Now what can you do? Well, if you try to do standard square root of x, this is just going to fail to compile because standard square root is not Constexpr yet. Well, I'm sure it'll fail to compile once we try to actually call it. So let's say Constexpr floats s is square root Constexpr of 3, right? Something like that. You've got to be kidding me. What is this? Is this some kind of wacky GCC extension? I'm out of here. This is what? Since when? It's not Constexpr. Okay, there we go. The Constexpr variable s must be initialized by a constant expression. And the problem is that we have a call to built-in squared f inside of standard squared, right? So this is not a constant expression. There we go. Yeah, I guess I should have enabled this pedantic or, you know, some warnings beyond just compilation errors in hindsight. But yes, this is not a constant expression. But we can kind of work around this issue using this magic function called if standard is constant evaluated. And here we'll see whether I've actually included the right thing. Oh, looks like I got lucky. So, hold on. No, it needs to be exactly the other way around. So, if we are not in a constant expression, then we just use standard squared, right? So we use the efficient version provided by the host library. You know, everything is working just fine. However, if we are in a constant expression, then we can define our own kind of pretty bad implementation right here. I don't know, like x. Yeah, I don't know how to do like a squared out of memory. Here, there you go. That's our squared function. Pretty epic, huh? So yeah, this is how you resolve this conundrum. So this is going to use the very efficient algorithm at runtime, but it's going to use the our own Constexpr implementation at compile time. And so yeah, this is pretty awesome. Yeah, I didn't see anything. Yeah, works for 4. You know, I need one test. I verified it. It works. Don't question it. So yeah, and then there's a question from chat. If Constexpr? Yeah, no, that's not gonna work out. Because the thing is that if you do if Constexpr here, right? If you do if Constexpr, it will basically always evaluate this to true. Because the inputs to if Constexpr needs to be a constant expression. So, you know, this is by consequence always true. So no, unfortunately, we can't just kind of discard another statement or so. We don't get the power of if Constexpr, we just get a regular if statement. And yeah, the compilers, you know, they point this out. Is constant evaluated will always evaluate to true in a manifestly constant evaluated expression. What a beautiful error message, telling you how it works in all detail. Okay, so let's continue with the next one. You know, I don't have an extreme amount of time to explain everything anymore, but yeah, basically placement new is something that you can't do in C++ 20 Constexpr. So you kind of have this issue that let's say you have a union, right? And you want to emplace something into it, right? So standard optional kind of needs to do this. Standard variant also needs to do this. So they have the storage, right? But you can kind of emplace stuff into it. So after everything has already been constructed, then you know, like you construct something after the fact with placement new. The problem is that's not allowed. That's not allowed in Constexpr. So standard constructed is kind of a workaround that allows standard optional and standard variant to work in a Constexpr context as well. So that's pretty cool. And then there's the problem that standard memcopy, sort of, which can be used for type punning. Yeah, we also can't do that because, as I've already kind of mentioned, the inputs to standard memcopy is a void pointer, and we can't convert something to a void pointer and from a void pointer in a constant expression, right? So the workaround for this is Bitcast, which can be used to kind of type pun something like, let's say, a float and an int. Very, very simple example. So includes the bits, that's where it's defined, and then we could do something like Constexpr float f is equal to standard bitcast float of, let's say, 3, right? And this would basically take the individual bits of this guy, right, of 3, and it would turn that into a float. It would just kind of reinterpret it. So this is called type punning. And yeah, if you didn't have compiler magic like standard bitcast, yeah, just it wouldn't be possible. You know, you can't really do that stuff with memcopy. And you can sort of see now we have this constant, it's a float, but yeah, it's just kind of 3. So I was hoping the assembly would be more insightful, but not really. Okay, so yeah, Constexpr QR squared. Yeah, you can implement the Quake inverse squared algorithm in C++ 20. Totally, you can do that. Okay, and let's finish with a bit of an outlook. C++ 23. What can you expect? So first of all, there's this idea of the const eval if statement, and the const eval if statement is very similar to standard is constant evaluated, you know, with an if, but it creates an immediate function context. So this is kind of important. Like, let's say you have some kind of, you know, const eval like function that takes an int n writes, I don't know, returns it as well. Very, very, very basic stuff. And you have a Constexpr function, Constexpr in fun2, I'm not very creative today, which calls return fun of n, and it's not going to work out because yeah. Hold on, let's get rid of this to simplify the warnings. But essentially the problem is we have a call to a const eval function fun, and that's not a constant expression here. Well, not always, and it has to always be. So with this proposal, I'm not sure if there are any ways to kind of have the proposals in here. I guess I'm not sure. I haven't really tested it out, but the way that it would work is that you can do if const eval of if const eval, and then you could do it inside of here, right? So this would then be permitted. That's the idea of this proposal. Just fixes kind of a mistake that has been made or a bit of a language defect. Another thing you can expect in C++23, this has also been accepted into the working draft, is to just fix some missing Constexpr in the standard library. So you still don't have a Constexpr standard optional and a standard variant in libstandard C++. I mean, not to mention the fact that we're still kind of waiting for Constexpr vector and Constexpr string. Yeah, there's just, you know, C++20 is still heavily in development, and these features are going to take some time to be completed. And yeah, last but not least, there's also this idea of Constexpr class. This has not been accepted into the working draft yet, might be. So here are the ideas that if we use Constexpr the way we use final for some class, then everything inside of it is also going to be implicitly Constexpr. So this just saves you a little bit of typing work. And I mean, the thing is that Constexpr is now so prolific, so many things are Constexpr now, it's basically the default. Right? So you have to put Constexpr on almost all the functions, and this just gets incredibly tedious. So yeah, this just kind of switches the defaults around. Very nice proposal. People are kind of trying to figure out how to type Constexpr less, and this is one possible approach to it, which doesn't seem so bad. Then there's the question, Constexpr vector, or did you mean Constexpr array? No, I meant Constexpr vector. Constexpr is, yeah, like standard vector, standard string, these are now Constexpr in C++20, as I've mentioned. Unique pointer is also Constexpr. I'm not sure about shared pointer, probably yes, but yeah. And yeah, that pretty much concludes this presentation. Due to answering some questions already, it has been a little bit overextended. In fact, our timer has kind of overflown. But yeah, if you're still interested in reading more and the slides, I'll just kind of post the slides once again in Twitch chat if you still haven't gotten the link. Right, so I recommend checking out the cppreference.com pages on the Constexpr specifier, then the named requirement literal type, constant expressions. Also, if you're really interested in what kind of new additions are going to be made to C++23, then you can check the paper submissions that are currently present and sort of follow the development process. And obviously, if you're really interested in how this works in depth and how this changed over time and you want to get all the details out of it, then yes, you should read the C++ standards. All of them are linked here. Those are the HTML versions, and we also have a working draft that has been HTMLified for C++23. And that is that. So with this, we basically conclude this presentation. We've already done a little bit of Q&A. But if you still have any questions, ask right away, or we're still here. Yeah, Twitch chat comments, this is not mobile compatible. Well, I didn't really design this to be mobile compatible. It's like, what, are you gonna open presentation slides on a mobile phone? I guess that's a reasonable thing to expect, but yeah. It would be very difficult to make this mobile friendly, then I probably couldn't hand type all the HTML anymore. Or it would be a lot more work. So yeah, if you still have some questions, if you're curious about the stuff in this presentation, then yeah, just ask away. I'll still be here for a couple of minutes. That was super interesting, thanks, but it was a bit too fast. Yeah, it was a bit fast to follow for me. Other than that, thanks a lot. Yeah, well, if you still have questions, you know, obviously you can go through the recorded video of this. It's going to be on this channel. You can check it out on YouTube as well. We have a YouTube channel. And if you're just generally interested in learning C++, and if you have questions about C++, yeah, you can also join our Discord server, and I'm sure that will help you understand quite a bit. So yeah, I'll just type out the link. Ah yeah, there it is already. So yeah. Then there's this question, why don't Goto in Constexpr? I'm pretty sure that it would be difficult for the compiler to kind of like have the sanitization work correctly if you had Gotos. I'm not 100% sure. It's just kind of a wacky thing that doesn't belong in a compile time context maybe. But yeah, I suspect it makes sanitization exceptionally difficult since, you know, the compiler needs to check for any undefined behavior. So that could happen. Oh yeah, it might. I mean, who even requests this feature anyways? You know, I think they would have made it work if it was a more popular feature, but people just kind of bash Goto so much anyways that might be for the best that it stays out of Constexpr functions. So there's yet another question. Am I correct in thinking Constexpr functions can be used both at compile time and runtime? Yeah, that's exactly the case. You can use them at compile time in a constant evaluated context. Perfectly fine. You can use them at runtime as well. And yeah, if you have to make a decision which one to, you know, based on the context you're currently in, then yeah, there's standard is constant evaluated. So you can even detect how you're running the Constexpr functions. The only functions that you can only run at compile time are const eval functions. That's the one restriction. And then there's another question from Hallelujah Fail. Should I just use an infinite loop with continue and a switch statement to jump everywhere? Well, it's still, you know, that's still not as powerful as Goto, is it now? Or is it? Well, I'm not sure if you can emulate all of Goto with that. Yeah, since the thing is that with Goto you can sort of, you know, like jump over initializations and stuff like that. Like you can jump backwards in code. It doesn't really do, it's not really the same with constructors and destructors involved and stuff like that when you need to correctly get rid of everything. I mean, you can jump back and forth like this with Goto. I don't know. I suspect, you know, if you desperately want Goto, then yeah, if you desperately want spaghetti code, you can kind of emulate it with a switch as well. That's possible. You can get most of the functionality of Goto this way, I imagine. And yeah, basically just kind of create a switch that has like enum switch cases as kind of labels, and then use continue after setting the one for the next one. You can kind of make it work. But yeah, I mean, as I've said, Goto is not a particularly popular feature. Maybe it's for the best that we don't have it in Constexpr. Yeah, there's a comment from Twitch chat. Goto is a nice way to handle errors. Well, the thing is, exceptions are also a pretty nice way to handle errors, and you don't have any. Well, you don't have errors either. In this, well, you don't have exceptions in Constexpr, right? That's another That's another thing about it. So error handling isn't really a thing that you do at compile time, because I mean at compile time you know everything, right? There's no user input, there's no wacky input from the operating system, there's no like hard drive failure or so that causes your IO to fail or something. There's just, you know, you don't really have errors at compile time now, do you? You kind of know everything. Everything is not at compile time, so yeah. Error handling is kind of a low priority. But, you know, that kind of brings me to an interesting one, namely no except, right? Because we don't have any exceptions at compile time. And before C++20, there was this really wacky trick to detect whether you're currently in a constant evaluated context or not. So let's say we have some kind of, you know, regular function, just dummy, whatever, right? Actually can be void, doesn't need any return type. It's completely irrelevant. So the idea is that in C++ like 11 and 14, let's get rid of a bunch of this stuff. Right, so the thing is that in C++ 11, the rule was that a function is always no except when evaluated at compile time. So if this is some kind of Constexpr dummy function, this is inevitably going to be no except. So what you can do is sort of, let's say, Constexpr, and you can use the no except operator to check whether a call to dummy is no except. And then depending on that, maybe return like n, otherwise plus plus n. That's interesting though. Wait, so what is it complaining about? If it's no except, then it's that. Well, what happens if I switch it? Did I mess it up or something? Okay, so what happens if we like do int Constexpr int x equals fun of 0? Well, that seems fine. I mean, if it's no except, and that should happen in a constant evaluated context. I'm kind of confused why this is working the way that it's working right now. We'll just kind of grab X in order to make this visible. Oh, that's very, very wacky. Huh. So it's saying that it's never no except is what it's telling me. I think that's what it's complaining about. Maybe Clang doesn't support this kind of stuff. Ah, there we go. Yeah, this now we're getting into no. Hold on, no, it's still 0. I might have messed this one up. No except operator. Now I don't want to give any false information here, so perhaps it's worth checking this out online. Because there was this kind of trick to do this stuff. Well, the example from CPP reference that they provide for this very, very strange phenomenon is this one. Ah, now I get it. I guess it, wait, does it need some overloading? No, this is just defining it. Bool B1. So here it's checking for the no acceptness of this. And this is never true, right? Because it's an undefined function. Oh, it's an undefined Constexpr function, so it's always false. And then once we define it, then it is true. Okay, so that was the behavior that I guess you can kind of use this for Constexpr detection. I'm not 100% sure, but yeah, this is wacky stuff. It got removed in C++ 17, and in C++ 20 we got standard is constant evaluated back. But yeah, if there are no more questions, and it seems like we've kind of handled most of it. So there is one more question. So, well, you just try to rickroll me. That's not very nice. You know what happens is if I open a link in a new tab, then I can see the YouTube title without it actually playing. It's nice try. Nice try. You're not gonna rickroll me, buddy. Okay. It seems like we're done here. We're going to see each other again, although the presenter is probably going to be somebody else next week. So tune in for next week's TC CPPCon. And as I've said, if you're interested in learning more about C++, then yeah, check out our Discord server. Have a good night or a day, depending on your time zone. See you.